Hi, Assalamualaikum. In this video, we are going to take a look at arithmetic instructions of AVR assembly language. For arithmetic operations, we will be dealing with signed or unsigned values. So, the Atmega 64 is an 8-bit microcontroller, so basically it processes 8-bit data at one time, and sometimes it can also process 16-bit data by combining two registers during the operation. So in this table we can see that we can see the difference between the unsigned and the signed values. So the unsigned values has only the positive range, and the signed value will have the negative and positive range. So if let's say we are dealing with a 1 byte number, so the 1 byte number, the decimal can be from 0 until 255 only. So basically, depending on how many bits the data have, the range will become the maximum range will become 2 to the power of number of bit minus 1, so we will get 255, and this is the hexadecimal representation. So 1 byte means that we have maximum 2 hexadecimal digits. So for 2 bytes or 16-bit unsigned, we have FFFF. We have 4 hexadecimal digits for the 2 byte data. And for the signed value, we have the negative range. And for negative value in hexadecimal, we can look at the most significant bit. So the highest negative value is negative 1 to 8, and then we have up until negative 1. So negative 1 to 8 is hexadecimal 80, and negative 1 is hexadecimal FF. So the positive range will become 0 until 7F, which is half of the positive range for the unsigned value, which is until 1 to 7. So this is for the 16-bit unsigned up until 65535, 2 to the power of 16 minus 1. And then we have the 16-bit unsigned with the negative range and also the positive range. For any microcontroller, the arithmetic operation is done by the ALU inside the CPU. So whenever there is an operation in ALU, there is one register that will be updated depending on the operation's result, which is called the status register. So the status register has 8 bits of data, or each of the bit is called a flag. We have at the most significant bit, we have the interrupt enable, and then at bit 6 we have the bit copy storage. For these two, we are not going to discuss in detail because for arithmetic operations, these 6 flags are the ones that will be affected depending on which instruction is executed. So generally we have at bit 5 the half carry. So the half carry is useful for the BCD arithmetic operation. Half carry will show the status whenever there is a carry from bit 3 to bit 4. And then we have the sign bit. So sign bit will depends on the operation of negative bit exclusive or the overflow bit. And then we have the V, the 2's complement overflow, which will be set if the result of the operation is out of range. And then we have the negative flag which indicates a negative result in arithmetic or logical operation. So basically, when the most significant bit of the result is 1, the negative bit will become 1. If it is 0, then the negative bit will become 0. And then we have the 0 flag, which indicates 0 result in arithmetic or logical operations. And then we have the carry flag, which indicates a carry or borrow in arithmetic or logical operations. So it means that whenever there is a carry or borrow at the most significant bit, the carry flag will become 1. In order to know how the processor treats the status register for any instruction, you can refer to the instruction set manual. For example, here, if let's say we have add instruction executed inside the program, the status register will be updated as stated in here, 6.2. So as you can see, inside the status register, it will show whether the flag will be changed or not according to the result. So whenever you see the bidirectional arrow, it means that the status of the flag will be affected depending on the result. So the description of the result will be shown here. For example, half carry will be set if there was a carry from bit 3 and cleared otherwise. And then we have the sign bit, which depends on the exclusive OR of the negative and overflow bit. And then we have the V, which will be set if 2's complement overflow resulted from the operation. And then we have negative flag set if the MSB or the most significant bit of the result is set. And then we have the 0 flag set if the result is 0. And then we have the carry flag, which will be set if there was a carry from MSB of the result. So whenever you are dealing with the arithmetic or logical operation, you can refer to the instruction set manual. And for most of the logical instructions, will only affect the AND negative and the 0 flag, and also the sign flag. And then the V flag will be false with 0, and other flags will not be affected. Let's look at the first example for add operation. So for add operation, we need to have the values that we want to add to be loaded inside the register first before the instruction can be executed. So let's say that we want to add the content of register. We want to add the values of F5 with 0B. So we can load the values first inside a register each. For example, here we load immediate register 21 with the first value, and then the register 22 with the second value. So what happened is the register will have the first and second value, and then we can call the add operation. So we can add the register of 21 with the register of 22, which will add the content of the registers together. So when F5 add with 0B, the result will become 0, 0, because F5 is negative 11 in decimal and 0B is 11 in decimal. So for add, the operation is the signed 8-bit values. So when the result is 0, obviously the Z flag will become 1 because the result is 0. And then what about the other flags? So the other flags will be updated depending on the bit by bit addition operation. So let's say we have F5. F is 1111, and then 5 is 10101, and then we have 0B. So B is 1011. So how the CPU add these values is bit by bit from right to left. So for here we have 1 plus 1, we have 1 0. So 1 plus 1 also 1 0, carry 1. And then 1 plus 1 also 1 0, carry 1. 1 0, carry 1. 1 0, carry 1. 1 0, carry 1, and so on. So after completed the 8 bits, we have a carry from the bit 7. So when we have the carry for bit 7, means that the carry bit will be set to 1. And then as you can see here, this is bit 3. And then bit 3, 1 plus 1 is 1 0. So from bit 3, we have a carry of 1. So basically this will indicate that there is a half carry. So half carry will become 1. So the status register will be updated to hexadecimal 23 because we have 0 0 for the first 2 significant bits, and then we have the half carry bit, which is 1. And then for the n is the negative, will depends on the most significant bit of the result. So n is 0 since it is positive. And then we have the z flag, which is 1, and then the c flag is 1. The v is 0 because it is correct, because negative 11 plus 11 is 0. And then s is the exclusive OR for n flag and v flag. So 0 0 exclusive OR, it will become 0. So that's why S register will be updated with the value of 2 3 in hexadecimal. Let's look at another example. Assume a memory location at hexadecimal 400 has a value of 33 hexa. Write a program to add the content of memory location 400 with a number of 55 and store the result in memory location 300. So basically in this question we have a memory location of hexa 400. So this is from the data space, and the content of the 400 is hexadecimal 33. So when we want to add something from the data space, we must load it into a register first before doing the addition. So basically first we need to load, we need to load from the address 400 into the register 2. So basically when we load from the address 400, it will take the content inside 500 and then load into the register. So basically after the instruction is executed, R2 will become hexadecimal 33. And then since we want to add with a number, so when we want to add with a number, this will become an immediate value. So we need to load an immediate value of 55 into register. So basically for immediate, we can only use from register 15 until 31. And then we have add instruction. So after they are loaded into the registers, then we can use the arithmetic operation. In this case, we use add R21 with R2. So R21 will be updated with the result, and then the register status register will also be updated depending on the result here. And then since we need to store the result in memory location 300, so the result is now at register 21, and then we want to store it inside a memory of address 300. We use STS, so the location is 300, and the content that we want to store is from R21, which is the result. So after this instruction is executed, the address of 300 will contains 88. And then we have the instruction of add with carry. This is usually used to add multi-byte numbers, since the ADD, the add instruction, can only process 1 byte values. So if let's say we want to add two 2-byte numbers of 3CE7 with 3B8D, we can use the add with carry. Since the operation of addition, if we do it manually, 3CE7 plus 3B8D, so the operation will start from the right side towards the left side. So first we add these two digits together, and then these two digits together, and then number 3 we add these two digits together, and so on. So sometimes when we are dealing with the 16-bit or 2-byte values, there will be a carry from here to here, from the first byte towards the second byte. So that's why we can use the add with carry whenever we are dealing with the more significant bytes. So let's look at this example. So first we want to load the values inside register. So since one register can only contain 1 byte, we can load the value, for example, the lower byte E7 and then the higher byte 3C. So we load it into the registers, and then we have the second number, the lower byte and the higher byte. So first we want to add the lower byte. So this is the lower byte, E7 and 8D. So E7 is register 16 and 8D register 18. So we use add, since for the first byte we don't have any carry to be added. So we use add R16 with R18, and then we store the result in R16. And then afterward, if there is a carry in this operation, the carry will be set to 1. So when we add with carry, so the value of the higher byte will be added, 3C plus 3B and carry. Since there is a carry from this operation, this add operation, so that's why we add with 1. So the result will be stored inside R17. So now we can see that the result of the higher byte is at R17, and then the result of the lower byte is at R16. So whenever you want to store the result, so let's say we want to store the result at 100 and at 101. So we can store the lower byte at 100 and the higher byte at 101 by using store the lower byte at 100 R16, and then we can store at 101 the higher byte R17. Next is the arithmetic operation of subtraction. So for subtraction, there are 5 instructions here. So we have the first one, subtract without carry. So all of the subtraction operations are also in the sign 8-bit values. So we have subtract without carry. So this is the operation. So RD minus RR, and then we store in RD, and these are all the status flag that will be affected after the execution of the instruction. And then we have subtract immediate with K as the immediate value, and then we have subtract with carry. So subtract with carry, RD minus RR, and then minus the carry. And then we have subtract immediate with carry, and also we have subtract immediate from word, means that we want to subtract a 16-bit value, and the 16-bit value will be stored inside 2 registers. Okay, the first example is subtract between 2 registers. So as usual, we need to load the numbers that we want to subtract inside the inside registers first, and then we can do the subtraction. So in this example, we subtract 3F from 2, 3. So when 3F minus 2, 3, the result is 1C, and then the status register will be updated with 0. And then we have subtract immediate. For subtract immediate, we want to subtract the register content with an immediate value. So now we want to subtract F4. F1111, 4 is 0, 1, 0, 0. And then we have 3F 0, 0, 1, 1, 1, 1, 1, 1. So for the subtraction, okay, from right to left, just like addition. So 0 minus 1, we need to borrow 1 from here. So 1, 0 minus 1, we got 1. And then since there is no value here, so we need to borrow from here. So 1 minus 1 becomes 0. And then we borrow again from here. 1, 0 minus 1 becomes 1. And then we need to borrow from bit 4 here. This becomes 0. This becomes 1. So this is 0. And then we borrow again. 0. 1, 0 minus 1 is 1. We borrow. 0, 1 minus 0, 1. So we have B5, and then the status register, which is 0, 0, 1, 1, 0, 1, 0, 0. The flags that will be set is the N flag, since we have 1 at the most significant bit. And then we have the half carry set because we have a borrow from bit 3 to bit 4. So we need to borrow from bit 3 to bit 4. So that's why each half carry become 1. And then we have the S, the sign bit becomes 1 because exclusive OR and with the overflow 1, 0 is 1. For a subtraction of 16-bit value, there is one instruction called subtract immediate from word, SBIW. So for this one, it will subtract an immediate value from a 2-byte value. So the 2-byte value comes from a register pair. So the register pair can start from register 24 or 26 or 28 or 30 with its higher register. So for example, here we use register 24. So the register 24 will hold the low byte, and then the register 25 will hold the higher byte. So from here, this example, let's say that register 25 will have 29 and 24 will have 17. So we want to subtract the 16-bit value of 2917 with a value of hexa 18. So we can use the operand of R25 colon R24 with the immediate value of 18. The immediate value can be from 0 until 63 in decimal. So after this instruction is executed, the result will be stored back inside the registers of R25 and R24. So R25 will hold the higher byte result and R24 will hold the lower byte result. And then the S register will be updated depending on the result. For multiplication, there are 6 instructions, but for this course, we will just focus on these two, the multiply sign unsigned and multiply signed. So for multiply unsigned, okay, in this example, we have the value of A9 and A5 and 15 to be multiplied together. So for multiplication, just like in the previous one here, for multiplication, the result will be stored inside R1 and R0, with R1 the higher byte and R0 the lower byte. So basically the multiplication is an 8-bit times 8-bit with the result of the 16-bit value. So here we have A9 times 15 will result with 0D. So from here, 0D will be stored inside R1, and then the DD result will be stored inside R0. And then the status register will be updated accordingly. Okay, for this you need to evaluate the program here. So basically how to evaluate is, for every line you need to be able to know which register is affected. For example, let's say we have LDI R20 hexa FF, so we have the value of FF loaded into R20, and then we have out DDRB R2. What happened here is DDRB will be loaded with R20, which is FF. So try to evaluate all the rest of the lines, and then you need to verify it back using the Atmel Studio 7.0. And then for the second exercise is, you need to write a program to add two 3-byte numbers. The first number located at registers R8 until R6, meaning that we have R8, R7 and R6 with the most significant byte at R8, and then we have another byte at R7 and then another byte at R6. And then the second number is located at data space of address 103, 102 and 101. So the the most significant byte is at 103, the next byte is at 102, and the least significant byte is at 101. So basically you have the these two 3-byte numbers and you want to add it together. So how do you need to write the program?